Hello everyone, and welcome back to another video. In today's video, we're going to be talking about a new topic, pretty unrelated from what we were doing the last 2 weeks with expected value. We're going to be going into analytic geometry. So, analytic geometry is sort of two fields of math fused together, and that would be mathematics that takes place on the Cartesian plane. So that would be like a graphs that you learn in school, like with the coordinates, which are ordered pairs, and geometry is the other topic. When we sort of do geometry on the Cartesian plane or on a graph, because in some cases it actually helps us out a lot because the Cartesian plane is pretty powerful and we know a lot of formulas, like we can find slope and distance between points, and there's some more complicated theorems that we'll learn about later on, but for the most part, what you need to understand is not every geometry problem can always be done or should be done in analytic geometry, but sometimes when you see that a Cartesian plane might be helpful, you can do what we're about to do and place a geometry problem onto a graph. So we have a problem and it says, let's say there's a square A, B, C, D. Point E is the midpoint of side CD in the square, and BE meets the diagonal AC at F. The area of the quadrilateral AFED is 45. So what is the area of the square? So I'm going to quickly draw the square, not on the Cartesian plane just yet, but just so we see what's going on. And this problem has multiple solutions, not all of which need to be done using graphs or analytic geometry. But I'm just going to draw this real quick. So it said E is the midpoint of CD, which would be the middle between points C and D. It says BE intersects the diagonal AC at point F. And we know that the area of the quadrilateral AFED, so that would be this, has an area of 45. So we can do some math different ways to figure out this answer, but what we notice is that anytime we have a square, it's sometimes really helpful to place that square on the Cartesian plane, and that's simply what analytic geometry is. And because we like to use the origin, because it's 0, 0, and it's sort of the center of our graph, we like to put a vertex usually at the origin. So maybe if we were using a triangle or if we were using a pentagon, we always want at least one vertex usually on that origin. And the reason that we can do this is because we can use unknowns as the coordinates of our vertex. So let me explain. So if I draw this square, you might be wondering, well, we don't know the coordinates, which is true, but we can say, so the coordinates of this vertex right here, we can call x sub 0, because we know the y coordinate is 0, and the x coordinate of the vertex we can call x, meaning the side length of this square is x, which means because it's a square, this distance is also x, so this point is x comma x, which means this point over here is also 0 comma x. So as you can see, we've already used analytic geometry to apply what we know about coordinates and simple stuff about the square, and we have 4 coordinates for our square. So now let's fill in the rest of what we know. So we know that we'll say this is D, A, B, C. So we know that point E is the midpoint of DC. So then what do we think the coordinate of E is? I'll give you a moment to think. So we know that the coordinate of C is x comma 0. We know that E is halfway to C. So that means that E is coordinates x over 2 comma 0. So now what else does the problem tell us? It tells us that EB, this blue line I have drawn, intersects the diagonal AC, and it meets at a point F. It also tells us that the area of this shaded region, which is a quadrilateral, has an area of 45. So this is 45. So now how can we use analytic geometry, what we know about graphs really, in the Cartesian plane, which the Cartesian plane is just the xy plane with our x-axis, y-axis. So how can we use the tools that we have when we're working with a graph? Well, first, for simplicity, we're going to use a little trick that you can use a lot of times in geometry problems, and that trick is to scale down the problem, or to make it simpler. So actually what we're going to do is we're going to assume the x coordinates and y coordinates of our circle. And you might be wondering, well then, where do we go from there? Well, if we say that we have a unit square, so that 1, 0 is the length, or the coordinate of C, and the length is 1, therefore, of the square, then B has to be 1, 1, and A has to be 0, 1. Of course, this means that the area of this shaded white quadrilateral can't be 45. But our plan, what we're going to do is we're going to say, well, how can we find the area of ADEF? And from that area, let's scale back up. So for instance, let's say that we found the area of ADEF to be 1/2. It used to be 45, now it's 1/2. So we've scaled it down by 90 times, right? Because 45 is 90 times bigger than 1/2, which means that if the area of our total square is 1, because remember we chose for the coordinates of our square to be 1, 0 at C, so the side length is 1, so the area is 1, meaning that means the area of the big square in our problem has to be 90. So you see how we use scaling in a geometry problem because it makes it really simple. So here we've given the coordinates of our circle to be 0, 1, 1, 1, 1, 0, and of course the origin, or D, is 0, 0. So now what we're going to do is we're going to find the equation of a line. So some of you may have learned this, but I'm going to go over it quickly for the people who haven't. So anytime you have 2 points, like C and A, you can connect them and you have a line. And a line is an infinite length. It goes on forever. We just have a segment of the line AC, but it does keep going forever if I extended it, right? Like this and like this. But for our problem, all we care about is AC, so the segment of our line. But the equation will be the same. And so the equation of a line means if you plug in any 2 coordinates into the equation, the equality must hold. So for instance, A, B are a line, right? If we connected A and B, it would be a segment of a line, but we could continue it. The equation of that line is just y equals 1. The reason for that being is if you plug in x, well, we can't, and you plug in any coordinate that has y equals 1, it has to belong to that line. So let's find the equation of the line AC. So to do this, first we want to find the slope of a line, and we call that lowercase m equals slope. A slope is simply the angle of your line. So as you can see, AB, the line, is a horizontal line, right? That means that its slope is 0. So when we're talking about the equations of lines, they're always in the form y equals mx plus b. M, I just talked about, is the slope. B is going to be your y-intercept. So I'll explain this a little bit more in a bit. So first, let's get back to slope. So slope, like I just said, is the angle. So for instance, when we were talking about AB, like I just said, the slope was 0. And the reason because is if we had m times x, well, m is 0, right? So that's why we had no x. But really, we could write this as 1 plus 0 times x because our slope is 0. The 1 is the y-intercept. And that simply means what is the coordinate of y when our line goes through the y-axis? So as you can see, it goes through the y-axis at a, which is 0, 1, so our y-intercept is 1. So to find the equation of a line, if we have 2 points, first we have to find the slope. Slope is rise over run, which some of you may have learned. We simply subtract the y-coordinates and divide that by the difference of the x-coordinates. So for A, first y-coordinate is 1, minus the y-coordinate of C, which is 0. Then the difference of the x-coordinates, so for A, that is 0, minus the x-coordinate of C, which is 1. So our slope is 1 over negative 1, which equals negative 1. So that's the slope of our line for AC. Again, the y-intercept is just going to be 1 because A is where it goes through the y-axis and the y-coordinate is 1. So the slope of our line is y equals negative x plus 1, right? Because we had m equals negative 1, or the slope, and b equals 1, the y-intercept. So this is the equation for the line AC. And we can check this because we can plug in the coordinates for 1, 0, or C. So if we plug it in, x equals 1, we get negative 1 plus 1, which does equal 0. So C does belong to our line. And if we plug it in for A, we plug in 0 for x, we get 1 equals 1. So A does belong to our line. So the equation of our line is correct. If we do the same thing now for line BE, we'll find that the equation of the line is y equals 2x minus 1. So quickly to go over that, what we need to do is we need to find the slope first. So that would be the y-coordinates subtracted. So for B, the y-coordinate is 1 minus the y-coordinate of E, which is 0, divided by the x-coordinate of 1 minus the x-coordinate of E, which is 1/2. So you see that if we do this, we get 1 over 1/2, which equals 2. So that's why the slope of the line BE equals 2. For the y-intercept, we can use what we just found, so the slope. So if we look at coordinate 1, 1, and we know that the slope is 2, that means every time we go over 1 unit to the right, we're going to go 2 units up, because slope is rise over run, or 2 divided by 1. So that means if we starting at 0, because for the x-coordinate, and we're going to go over 1 unit to the right, we have to go up 2 units. And so we can see that the y-intercept is negative 1, because from negative 1, if we went up 2 units, we would get to 1, which is the coordinate of B. Now we can do something really cool, and we can find the intersection of these two lines. So as you can see, they intersect at F. And to do this, we solve a system of equations. So some of you may have learned about this, but this simply means there's going to be a coordinate which works for both equations. So if you plugged in C, or the coordinates for C, to the line for AC, it would work. But if you plugged it in for BE, it would not work. However, if you plugged in the coordinates of F, because F is on both lines, those coordinates are going to satisfy both equations. So what we do is we set the equations equal. And because they both have y on the left, we can just set the x parts equal, and we get negative x plus 1 equals 2x minus 1, and we get 3x equals 2, which means the x-coordinate of F is 2/3, and then plugging this x-coordinate into either of the equations, because it'll satisfy both, we solve for y, and we get 2/3. Or sorry, we get 1/3 for the y-coordinate. So the coordinates of F are 2/3, 1/3. So now that we know the coordinates of F, we can find the area of this little triangle EFC. The height of that triangle is going to be the y-coordinate of F, because that's what a y-coordinate is. It's the height from the x-axis up to that point. So we have the area of a triangle is 1/2 base times height. So the base is the distance EC, which we know is 1/2. So it's 1/2 times 1/2 times the height, which is 1/3. So that will equal 1 over 12 to be the area of FEC. So now let's try and find the area of that quadrilateral ADEF. We know that ADC is a triangle, and it's going to be half the area of our square ABCD because the line AC splits it right down the middle. So we know that the area of our square is 1, so the area of triangle ADC is 1/2. So now we can subtract because we know the area of, I'll shade in the region, we know the area of this triangle right here, and we know the area of the big triangle ADC. So the difference of that is the quadrilateral ADEF, right? We can subtract, and we're left with the green stuff. So we do 1/2 minus 1/12. That gives us 5 over 12. And so now we can scale back up to our original problem. So in the original problem, we had ADEF with an area of 45. But here in our smaller example, when we use a unit square for ABCD, the area of the quadrilateral ADEF is 5 over 12. So how much bigger is it? Well, we can just divide. We do 45 divided by 5 over 12, and we get 108. So that's actually going to be the answer because that means that the unit square is 108 times smaller than in our actual problem. And of course, 108 times 1 equals 108. So the area of our square indeed equals 108 when we've solved the problem. So this took a little bit of explaining, but that's because we were sort of working through how to solve for the equation of a line, how to find the intersection of two lines using the system of equations, how to use scaling. But in general, you can see how powerful analytic geometry is because of how much we know about lines and how many theorems we have. So often, analytic geometry is going to come in handy if you get stuck in a geometry problem. So we're going to give you guys a few problems to work through that relate to analytic geometry. So of course, you'll know to apply it. But even when you're using problems and you're not positive that they're analytic geometry problems, you should always consider it because maybe it'll help you out. So I hope that you guys learned something. And of course, you can watch through the video a couple times because I know I went kind of fast over things. But you can definitely reach out to us via email and attend the Zoom meetings if you have any questions about analytic geometry or about the problem set that we're going to send out. And as always, thank you for watching, and I hope you enjoy your weekend, and we'll see you, I believe, on Thursday. Bye.